Okay, so at this point we have what? We have C dt d theta plus K times T equals G plus the term we still haven't tackled is this boundary weighted heat flux term. So this is the heat flux normal to the boundary, integrated all along the boundary of our computational domain. Right? If you remember, it looked like this. This was Q double prime N, and this could be composed of both some specified heat flux or convection, H times T infinity minus T. So this is the guy we still have yet to deal with, and that's what we'll deal with today. This heat flux normal to the boundary is specified heat flux plus H times T infinity minus T, where this is our approximate temperature distribution. And for us, we said that T is equal to what? It's equal to W transpose times T. Right? This was our weighting functions, and that's our vector of temperatures at each node. So this then becomes the heat flux normal to the boundary is the specified heat flux plus H times T infinity minus H times W transpose times T. So this is what I have to insert up into here, right? And I get then that we have the integral over the boundary. This is not an area integral, this is integral all the way along this boundary. The integral over the boundary of W times the specified heat flux, ds, so that's the first one, plus the integral over the boundary of W times H times T infinity, ds, minus the integral over the boundary of, what is this one? I guess it would be H times W transpose times T times ds. Right, so that's this one here. So this ends up being what in finite differences we call our specified heat flux vector. This ends up being H times T infinity. This is also a vector. And this ends up being H times T. So our convection matrix multiplied by our temperature vector. So these look familiar once we figure out how to construct them. And the way that we have to do these integrals is boundary segment by boundary segment, right? So if this is our mesh, we'll just draw a simple one here, like this. And so we'll come along here and sort of join these together to make a simple mesh like this. So what we had done to make C and K and G is do an area integral by area integral of all these elements. What I have to do to get these guys is do boundary segment by boundary segment by boundary segment by boundary segment all the way around, right? So this guy has n equals, I think there's 10 nodes. Right? There's NE equals 11 elements. And the last thing we have to keep track of is MB, which is the number of boundary segments. So this is 1, 2, 3, 4, 6, 7 boundary segments. 7 boundary segments. Right, so when I'm constructing these guys, I'm going to do it in 7 steps, versus when I was constructing C and K and G, I had to do that in 11 steps for this particular mesh. Alright, so it's the same idea here. This is our global QS vector. We're going to split it up into our boundary QS vector. Right? So we're going to say that Q is equal to the summation from B equal 1 to the number of boundaries of the integral over each boundary segment of W times QS ds. Right? So this is our our boundary segment heat flux vector, which is what we actually have to learn how to construct, and then this is the total vector, right? And if I keep going, we're going to have the summation from b equal 1 to the number of boundary segments of this will be the integral over a single boundary segment, w times h times t infinity ds. So this is h t infinity for b, and this is h t infinity. And finally, minus the summation from b equal 1 to the number of boundary segments of the integral over each boundary segment of h times w transpose times t ds. Right, so this is what I have to figure out. This is h times the boundary times t, and then this is h times t. So we'll do each of these one at a time. Okay, so let's start with the heat flux vector qs b, which we said is equal to the integral over some boundary segment b of w times the heat flux times ds. So first of all, we're going to require that the heat flux over each boundary segment be constant, even though it might change as we move along the boundary. So this we can bring out. And this is going to be then equal to the heat flux along boundary segment b times the integral along that boundary segment of w times ds. Now we got to think about what it means to be integrating along a certain boundary segment. So this is some boundary segment defined by node I and node j. And there's some node k up here. Here's an element, right? We don't care about the element, we care about this boundary segment right there. So this goes off and does some other things. So along this boundary segment, only wi and wj are non-zero, right? In this element, I, j, and k are all non-zero, but down here, this is the contour of wk equal to 0. So only I and j are non-zero. In fact, if I wanted to sketch wi, it would start here at 1, and when I got over here, this is s, this would be 0. So it would look something like this. Right? This is s moving from right to left. This is s equals 0. This would be s equal sij, where this is the distance that this boundary segment makes up. If I did wj, it would look just the opposite. This is s, this is wj, this is 1, this is 0. Over here, wj is 1, and it goes to 0. Right? So what this looks like then is, this is a big vector that only has two non-zero terms, right? So qsb is equal to qs, and then here I have a vector, right? And in row I, this is row I, I'll have the integral of wi ds, and in row j, I'll have the integral wj ds. Right? So I have to now figure out how to evaluate these two integrals along this boundary. Right? So the integral along boundary segment b of wi ds is basically, if you think about it, the integral of this function along this curve. It's just the area underneath this curve right here. So this is going to be equal to 1/2 sij. And the same thing here. The integral of wj ds is the area under this curve, and that's equal to 1/2 sij as well. Okay, so my rule then for constructing the boundary specified heat flux vector is, let's see, if I substitute this and this up into here, I get the heat flux along that boundary multiplied by the length of the boundary divided by 2, and then I have a big vector that is mostly zeros except for in row I, and in row j I have a 1. And again, you can see that what I'm doing is I'm taking this heat transfer that occurs along this boundary, and I'm dividing it by 2, and I'm assigning half of it to this node and half of it to this node. So let's look at the last term, right, which is this one. We have the summation from B equals 1 to the number of boundaries of H times W transpose times T ds. So the first thing we can do is take T out, right, because T is the temperature at every node, and those can only be a function of time. So this becomes summation from B equals 1 to the number of boundaries of the integral over the boundary. The integral over the boundary of H times W transpose ds. Well, this whole thing is multiplied by T. So this becomes our convection matrix, actually. Right? And then this guy right here would be our boundary convection matrix. Right? So we're going to have to figure out how to build our boundary convection matrix. Our boundary convection matrix is the integral over a boundary segment of H times W transpose ds. Right? So again, the heat transfer coefficient might vary as you move along the boundary, but along any boundary segment it's going to have to be constant. So H boundary is the heat transfer coefficient along that boundary times the integral of W times W transpose ds. Right? So along a boundary, again, only 2 of these weighting functions are going to not be equal to 0. So we're going to have something that looks like this. H boundary is equal to H boundary, and we'll have, what would this look like? It's going to be W, which is going to be something that is like this, or you might have a Wi and a Wj, and a W transpose, which is going to be something that looks like this. You have a Wi and a Wj. So we're going to have 4 non-zero elements in this big n by n vector. It's going to look like this. It's going to be n by n, and in row I and j, and in columns I and j, we'll have non-zero elements. So here in row I and column I, we'll have, I guess it'll be Wi squared ds along boundary segment B. This would be Wi Wj ds. This would be Wj Wi ds, and this would be Wj squared ds. So again, you can see the convection matrix is going to be symmetric. It's going to be pretty sparse. We have to figure out how to carry out these different integrals. We'll start by remembering what Wi and Wj look like, right? So along boundary segment Ij, so this is I and this is j, along this boundary segment, I'm going to have Wi is going to start at 1 and go to 0. So Wi would be 1 minus s over Sij. So this is s, and this is Sij. Wi is going to start at 1 and go to 0. That's what this does. Wj is going to be starting at 0 and going to 1. So this is going to be just s over Sij. So these are the actual functions that I can substitute up into these different integrals to do them. So let's do this one to start with. We have the integral from boundary segment B of Wi squared ds. Right, so if I plug this guy into here, I get this is the integral of 1 minus s over Sij squared ds. And I want to integrate from s equals 0 to Sij. And so this ends up being the integral from 0 to Sij of, I guess it would be 1 minus 2 times s over Sij plus s squared over Sij squared ds, which is equal to s this is s squared over 2, so this is minus s squared over sij, and this would be plus s cubed over 3 sij, evaluated between the limits of sij and 0. So what is this then? This is sij times, this would be 1 minus 1 plus 1/3. So this is just sij over 3. So what I would plug into here is sij over 3. Now we can do the same thing for wi times wj. It's as simple as carrying out the integral of, I guess it would be 1 minus s over sij multiplied by s over sij from 0 to sij. And I think we can all do this. This ends up being sij divided by 6. So that's what I would plug into actually here and here. And this ends up also just being sij over 3. So you can see how this works. And my boundary convection matrix is this n by n matrix, where there's non-zero elements in rows I and j, and in columns I and j, like this. And we'll multiply the whole thing by the heat transfer coefficient on the boundary times Sij, and here we're going to have what? We're going to have 1/3 and 1/6 and 1/6 and 1/3, and that's how you construct H, right? You do this boundary segment by boundary segment, and you're just adding them up. H is equal to the summation from B equal 1 to the number of boundaries of HB. Alright, so let's do the last term here, which is this one. B equal 1 to the number of boundaries of the integral, or the boundary segment of W times H times T infinity ds. And again, we're going to call this HT infinity. This is our global HT infinity vector. This guy then is our boundary segment HT infinity vector. And this is what we have to learn how to deal with along any boundary. The first thing we're going to do is require that the heat transfer coefficient and the free stream temperature, the fluid temperature, be constant. So this is HT infinity along the boundary. So we're then just integrating the weighting function with respect to ds. And along any boundary, there's only two non-zero elements inside of here, wi and wj. If the boundary is defined by nodes I and j, so this ends up being h times t infinity b is equal to hb t infinity b. And this ends up being then the integral of wi ds along boundary segment b, and the integral of wj ds on boundary segment b. And of course, this is then just the area under the curve of wi and the area under the curve of wj. And remembering once again that this is what wi looks like. It starts at 1, goes down to 0, and this distance is sij. And this must just be sij divided by 2. So h times t infinity for the boundary is h boundary t infinity boundary times sij, and we have a 1/2 in row I and a 1/2 in row j. And if I want this global one, it's just a matter of adding up all these boundary segment ones. HT infinity is summation from B equal 1 to the number of boundaries of HT infinity of each boundary. So at this point we're done, at least for this problem. Right? We're left with this system of equations, which looks like what we worked with for a long time for finite differences. C dt d theta plus k times t equals g plus the specified heat flux vector minus h times t minus h t infinity, right? This guy, and this guy, we assemble element by element. So this is assembled in 1 to n sub e steps. We're adding these up. This guy, and this guy, these are assembled boundary segment by boundary segment. So assembled in 1 to n sub b steps, and we're just adding them up. But the dimension is the same, right? All of these are, this is n by n, where n is the number of nodes, n by n, n by 1. You know, even though we're assembling them in n e steps, they're still n by n. The same thing here. This is n by 1, this is n by n, and this is n by 1. So even though we're assembling them in n sub b steps, the dimension is equal to the number of nodes. So we can rearrange this, and we get to c times dt d theta plus k plus h times t equals g plus q sub s plus h times t infinity. Right? This is our stiffness matrix. This is our thermal loading vector. Right? And we can do all the stuff that we've done previously in finite differences to solve these now using finite elements. And the only thing is that we need to be able to construct these differently, right? So we'll have a mesh for a finite element, and we now have rules for how we construct each of these, you know, either one element at a time or one boundary segment at a time. And that's really the important thing that we've done over the last few lectures, is come up with those rules.